Welcome everyone, thanks for coming to my talk about computer algebra in Scala. I don't know if everyone reminds of what is a GCD. This is Euclid's algorithm for computing GCD. This is one of my first designs here in Java, which computes a polynomial GCD. So it's verbose, right? Because in Java we didn't have type inference, so we have to indicate the type of our parameters and our return type. And to do this kind of thing, we have to define, for example, to have this remainder method available, which is the case for our type here, polynomial. This is more recent instance of the same Euclid algorithm in Scala. So one improvement besides type inference is that we can use symbolic methods here for the remainder method. I made it tail recursive instead of using a while. What else? Yes, it's generic. In Java, I could have a generic example also, but let's say it's available in Scala, so it's good. Our type T here will have available this remainder method at some condition. For example, if T extends some type with a % method here, then it will work. Or we could also have a type class which with an extension method for our remainder method here. In the first case, I will name it a wrapper approach for enrichment to provide a type with an operator like this one. And in the second case, I call it the type class approach. I won't teach you what is a static type. Just let us say that sometimes it's too strict, meaning if we have a polynomial type and we define a method, a function to add this polynomial, to add, let's say, two polynomials. One is formally also a polynomial in z of x, instead if it's a trivial one, but it will fail, right? Because the type system will not recognize it as a polynomial. To restore flexibility, we need a mechanism called numeric promotion, which already exists for built-in type. For example, you can add a int and a long in Scala, or in Java, or in C, on every language. But for custom types, in Scala, we'll be able to use implicit conversion for that. In computer algebra, custom types are not an option. We absolutely need to, for example, a type like Java math big integer for multi-precision arithmetic. But in Java, the syntax is verbose. We don't have a symbolic method, we just have a literal one. So we need enrichment to handle a numeric type with arithmetic operator. Numeric promotion, as I said, is the fact to leave an operand value from a subset type to the type of the other operand. I will now detail the two different approaches. The wrapper type, or also named object-oriented, and the type class base approach. The wrapper approach, which is used, for example, for the BigInt type of Scala, which has an underlying big integer, and which will route a symbolic method to the literal method of the Java type. With a type class, you define here an extension method with the symbolic operator, as in the case of big integer in terms of the literal method. And then when you use a Java big integer, by virtue of having this instance in scope, everything will be like the origin type has now a symbolic plus operator. That was for enrichment. Now for numeric promotion. You'll see there will be an interaction between the two concepts that it's not easy to get right. So in the wrapper case, we define a value A of type BigInt, and then we add some value which needs to be promoted to numerically. The implicit mechanism will look in the so-called implicit scope of int to this structural type here. Sorry, there's two cases on the right and on the left. On the right, implicit conversion looks in the implicit scope of int to BigInt, which includes BigInt's companion object, which has this implicit function here into to BigInt. So it converts one to BigInt, and the operation can succeed. In the left case, the implicit scope is the one of this type here, structural, which is again BigInt companion, and it works too. In the type class case, however, this is what is happening. This is our type class here, a ring. It's simplified. Just the plus method is shown. For a ring, you will have multiply and also some unary method like 1, 0, things like that. But this is simplified. Here we have an instance of our type class for still Java big integer. Here we have the implicit conversion from int to big integer and the implementation of our plus operator. We have this import here to have the conversion in scope. We define a value of a big integer type. On the right hand, it works, but not on the left side. So this is a problem. In the type class approach, numeric promotion fail on the left. It turns out if, in addition to the implicit conversion, we also import asterisk, means everything but among others the method itself, plus, then it recovers the successful operation. So in the following, we will try everything to avoid to not have to import the operator, because it's ugly. It's it doesn't work. Not satisfactory. Now that we've seen the type class functioning for with one instance, we can look at what happens if we have two different types with a type class, with a ring type class for both. Make the ugly import, but for the moment that's all that we have. On the right, it works, but on the left here, we have a problem of to solve the overloaded alternative. So what can we do? I substituted to plus a method that is not an operator of int here to try to understand what's going on. So if I use plus plus as an operator, so int has nothing to do with it, so we can know more about the problem. And the problem at the heart is one of implicit resolution problem. It's ambiguous to the implicit resolution process, whereas we know that one instance is more basically there's one instance that's supposed to work in each case, and it doesn't know how to pick it. So it's a limitation of implicit resolution, and unfortunately, we'll have to live with it. I would now like to take a step back and look a bit at historical perspective on computer algebra on statically typed language like Scala, and what Scala can bring to the domain of computer algebra, and conversely. So the fact to do computer algebra with a statically typed language, as a name, it's named categorical view of computer algebra. The pioneer was Axiom in the 90s with the Aldor language, but it's a specific language for computer algebra. And the first attempts to do computer algebra with general purpose language was also in 1990, in the 90s, sorry, with MAS and the JAS for Java Algebra System by Hans Kredel. Who translated a set of computer algebra libraries in Modulado and Java. As an aside, Modulado, as you may know, was invented by Niklaus Wirtz, the teacher of Martin Odorsky. So maybe you can see structure emerging. One other interesting work in this domain of categorical view of computer algebra is the one of Serge Mejveliani in Haskell. I started SCAS in 2010, and since then Mejveliani has ported his whole DocCon for domain constructor in Agda to use dependent types, but I did not look into it, and clearly is in advance. So it's interesting, but it's quite involved stuff. And yes, in 2008, I have written an article with Hans Kredel to try and propose let's say a way to use a Java library with a scripting language, meaning Java is statically typed, of course, so it's in our opinion perfect for this kind of application of computer algebra, but for the interface we need to have an untyped language. So there are versions of our scripting interface in Jython, in JRuby, and also in this article I propose to use Scala, which is not a scripting language proper, but it's so concise with its type inference and everything that it can be used, and it has a REPL. It can be used also for scripting. That was my thesis. So why Scala? In the Scala documentation for type classes, you have this example here, which is the exact same thing you could have for computer algebra example. What I mean is my algebraic structure library for my library SCAS is not different from this early schema, not much different. Here you recognize semigroup and monoid. Here, ring, which is the cornerstone of your structure if you want to make computer algebra. So it's just monoid crossed with abelian group. Abelian group is for plus, if you want. Monoid is for multiply. Sorry, semigroup is for multiply. Monoid will give you 1. And abelian group also gives you 0. So with a ring, you have everything. You have integers and you have polynomials. So you have, and you can nest polynomials, meaning you can have polynomials over the integers, for example, but also polynomial over polynomials, etc. Speaking of polynomial, symbolic computation is niche. You don't need this in your day-to-day work, I think. But as for numeric applications, they can take advantage of the same algebraic structure. For example, like linear algebra. Here you see you have module, vector space, algebra, for an algebra of square matrices, for example. Also numeric, you have complex numbers, and once we have a good implementation of complex number, we could integrate it in the standard library. I think there's no many languages with a built-in complex number implementation, maybe Fortran, but I don't know of others. So this will be an application. And third application, interesting for informaticians, is logic, Boolean algebra. Here are some tautologies that can be computed by a small interpreter I wrote for my library. Maybe some of you will recognize the third one here, or not. Sorry? It's concurrent continuation, the type. It's a tautology in Boolean algebra, but not in intuitionistic logic, which means that you can add this type or remove it from your language as you wish. So there's a question of I don't remember, it's undecidable. But if you have it, it's a type of the CoLCC, concurrent continuation. So it's something you can use if you use continuations. What computer algebra can bring for Scala, for language like Scala. This is an implementation of GCD again, but in the case, in the multivariate case. So again, maybe some of you can recognize what this thing here is. it's polymorphic function. There are also higher candidate types. The algorithm is, if I have more than one variable, then I will split my polynomial ring in two. So I will have a polynomial in one variable over a polynomial of the remaining variables. And then I convert and I compute the GCD and convert back. If I have one variable, I will apply univariate GCD here, which is abstract, meaning this is abstracted over the specific algorithm you want to use for GCDs. And yes, that's it. So it's computer algebra will make you use advanced features of your language, like stretch the limit a bit of your type system in some cases. This is yet another way of computing a multivariate GCD by Grobner basis here on a module, which is like a vector for polynomials. And what's interesting is that it looks very, very similar to the corresponding paper. You have a matrix here with PQ 1, 0, 1, which is here. And in the end, you compute the quotient P over V here. So a powerful language like Scala allows you to basically paraphrase your corresponding scientific paper. This is, by the way, a paper relatively recent, 2016, by Daniel Lichtblau from Wolfram Research. We developed Mathematica. So they took some time to get it right, computing a GCD by Grobner basis. But yes, sorry, I will say a bit about Grobner basis for those of you. I imagine very few people here now know the concept. It's like a mix between, on the one hand, Gaussian elimination for multivariate but linear case, and the computation of a GCD in the univariate but degree more than one case. So it's like a Swiss knife of computer algebra. And it turns out you can, which seems logic, but you can compute a multivariate GCD with it, but you have to come up with the exact algorithm was finally found in 2016. So back to our implicit resolution problem. So one first remark is that there's lots of cases where we have, for example, we have several type class instances, but these are nested. For example, a polynomial in a coefficient C. And in this case, so here we define the type class instance, we recall the type class instance for big integer. We define a mock polynomial for a coefficient of type C. Here we define a type class instance for a polynomial ring over the integer. The type class for polynomial has this definition of the plus method, which is based on the same method but for the coefficient type here. And we've also here the conversion from something that can be converted to C, then you get a polynomial in C. We can avoid the collision of the two instances by importing only the operator for the top ring here. S is for the polynomial, R is for the integers. So if we forget about integers and just import plus for polynomial, then it works. But everything is lifted to the top ring. For example, here 1 is lifted to first, let's say A, which is a big integer, is lifted to the polynomial ring, and 1 also 1. So it's it would not be necessary. You could just lift 1 to big integer and make the operation in the integer. But it works. Not perfect, but I make a little digression about the new into keyword. For implicit conversion to work, in the future, we'll have to declare it and to mark at the definition site which arguments can undergo implicit conversion, like this. I will now present an alternative to implicit conversion, which will do exactly the same thing, but without implicit conversion. First, I will make a redirection because as the signature will be altered, it's cleaner to take a literal method here to be able to implement our operation and to put the gory details of implicit conversion in the symbolic one here. So where you would have put into in the forthcoming implicit conversion proposed scheme, what I do is put here a context bound for this type class. It's not very complicated. It is isomorphic to the into keyword, more or less. At one point, I thought maybe into was a syntactic sugar for such mechanism, but it's a bit different, but they work about the same. So here you have this tilde modifier which allows you to redirect to your method without implicit conversion. So this is our former example with normal implicit conversion. And this is the new mechanism which works without needing to import the operator. Turns out. I don't know why, but it's okay. So it's an opportunity. Then what happens if we have several instances? Since I don't import it anymore, we cannot use this to choose the one and to lift to the top ring as mentioned. So the trick that I found is to provide an instance of the type class inside itself, which will be imported by the statement here, which was just for the implicit conversion. So instead of having a given instance, I just have an object, a normal object, non-implicit, and I will put it in the implicit scopes through this import here. But since I already had an import, it's a simple thing, and it will restore the a working condition for the case with several instances, because as the given here is named, they will supersede one another, meaning in the end you will only have the one for the top ring, for the polynomial ring, which will be active at the time, and it will restore the functioning. There's one case where this does not work. If you remember, this is a definition of our plus operation in the polynomial case, which is based on coefficient arithmetic, and we cannot lift to the polynomial ring, otherwise it would lead to a circular definition, as you can see. So we're still we still have to import the operator for the coefficient ring. How to solve this? Well, we drop numeric promotion on the left altogether. Okay? We just give up. And we can recover it in a subclass. Okay? So in the end, we'll have split our algebraic structure hierarchy in two. One with support for left-handed numeric promotion and the one without, the other one without. This is an example. This is the implementation of complex numbers in my library. Class impl here in the so-called parent plane without left promotion, and object complex is in the conversion plane, that is with conversion on the left. And for example, in the parent plane, here you can do operations which do not need numeric promotion, but if you want numeric promotion on the left, you have to be in the conversion plane here. As you can see, it's indented out, meaning it's in the object complex here for support for promotion on the left, which allows us to give this defining equation for complex number here, meaning a nice mathematical notation, which was the goal. So in summary, we make no concession on static types, meaning no typecasts. We want the functional approach, meaning type class based rather than object oriented, because it's more flexible, efficient. You don't have a wrapper, so you don't box. You can work with primitive types, but it mandates an operator import. We introduce a context-bound approach to implicit conversion, which allows us to omit the operator import. But in case there's several instances we have to choose, then we define given instance as member field of their own type class, which allows to supersede one another and to omit imports, even in the case where there are several instances. In case of nested algebraic structure, meaning you need to compute in, for example, the coefficient ring inside the polynomial ring definition, then we have no choice. We have to split the type class hierarchy to isolate left-handed promotion. So this is a lot of contortion, but it's still the price to pay for a nice mathematical notation in a statically typed language. Finish. Thanks.